All right. I actually think of the ones that I asked you to do. This one's the trickier one, because it may take you a little bit to figure out where U should be and which one U should be. The idea here is that we have, some of you might have put U as 2t plus 1, but we actually have even more going on here, where I'm going to say that U should be the cosine of 2t plus 1. And again, two reasons I chose cosine. Number one, the derivative of cosine, which is a negative sign, has something pretty close to it somewhere else in the problem. And number two, it's true that, sine has its derivative cosine somewhere else in the problem. So you might be thinking, why would I choose cosine and not sine? But our other big clue, don't forget, is that the function is inside of another function. So I chose cosine because it's the one that is getting squared. Oh, I don't have this -2 over here. Let's move it. And so when we do the U substitution, there's what it should look like. So this sine of 2t plus 1 dt on the top becomes just du. And the cosine of 2t plus 1 getting squared just becomes u squared. And the -1/2 comes out in front of the antiderivative. There's your antiderivative. Makes it positive. 2 is on the bottom. Substitute for u plus c. Now, there is actually another way that you can do this without a u substitution. That looks very complicated, but check this out. Let me rewrite this so that you can see this. Sine of x over cosine squared of x would equal sine of x over cosine of x times 1 over cosine of x. That means the same thing. So if I just split it up in terms of sines and cosines, well, sine over cosine is tangent. 1 over cosine is secant. And so this is really just a very fancy way of writing secant tangent. And antiderivative of secant tangent is just secant. And then 1/2 to undo the chain rule, plus c, which is the same thing that I got up here. It's just writing 1 over cosine instead of writing secant. So one of two ways to do it, either with the u substitution of making u cosine and not dealing with the trig at all, or deal with the trig and simplify the trig. One of those two ways that you can do that one. I'm going to drill through all three of these, and then I'm going to stop to see if we have questions. Next one. Dx over x, natural log of x. We were talking about how it might be easier to split off this integral, so I'm going to write this as 1 over x times 1 over natural log of x dx. And hopefully that makes it easier to see what u is going to end up being. U is going to end up being natural log. Why? Because something's happening to it. It's on the bottom of a fraction. And the derivative of natural log, which is 1 over x, is somewhere else in the problem. So we have 1 over u du. Just to back that up a little bit. There's u. And then this is du. That all matches. And so don't forget, when we take the antiderivative of 1 over u, that's going to be natural log. And something I'm going to remind you here is that natural log in the antiderivative part of it should have an absolute value. And so it should be natural log of the absolute value of u, which, what was u? It was natural log of x. So this is the natural log of the absolute value of the natural log of x plus c. Let's take a look at one more of these. This one, I'm not going to go through the whole process. I'm just going to talk about u and du. If this were just a 1 over x squared plus 1, then the antiderivative would just be inverse tangent. But bad news, we have an x up there. And so this is where my clue of the derivative is somewhere else in the problem is going to come in handy. Because du 2x dx. Oh, but we want it to be x dx. We want it to match with x dx. So 1/2 du equals x dx. So we have a du on top. 1/2 comes out in front. And then we just have a u on the bottom. There's what the answer ends up being. All right, this one I skipped before because it's quite a bit tougher. And the reason that it's harder is because it seems a bit more pulled out of nowhere what u ends up being. So I want to kind of talk through how you can figure out that we want u to be x over 3. Because it's a little bit different. The derivative of x over 3 is not anywhere in the problem. And so that makes it harder to work with and to try and figure out what u should end up being. So I want to talk through how that's going to work. And I'm going to do that by working backwards for what I want to end up with when I do my u substitution. Because this looks really close to tangent inverse. If I just had an x squared plus 1 here, then I would be in great shape and I would just have inverse tangent. So my goal is to have maybe something out in front here and for it to come out to be u squared plus 1. And let's see, we're going to work backwards here to say that the integral I would want in that case would be, let's see, the way that I could get this to turn into a 1 is if I could factor out a 9 and then make this u squared plus 1. Oh, well, that means the 1/9 is what comes out in front of the integral here. Again, what I'm doing is that I'm working backwards to show you how u has to be x over 3. Because this is the one that people always get stuck with what to make u. This one's tricky to figure out what to make u. Well then, that would result in 1 over, du. That would result in 1 over 9u squared plus 9. du. And to back up a little more, that would mean that this would need to be plus 9, sorry. A 3u inside of here that I'm having to square. In other words, in order to get this 9 to factor out so that I just have a u squared plus 1 and I can just use my inverse tangent, I know that my goal is this inverse tangent with the u squared plus 1 on the bottom. To do that, a 9 had to be factored out. To do that, I had to start with a 9u squared here. To do that, what needs to be squared? 3u. So in other words, x needs to equal 3u. Or, to put it right in another way, u has to be x over 3. du or we'll do it this way, 3 du equals dx. Or if you're going from u, du equals 1/3 dx, and we don't have the 1/3 there, so 3 du equals dx. That means we have a 3 here out in front of the integral. Three times 1/9 means a 1/3 comes out in front here. And antiderivative of this is just inverse tangent of u, which let's substitute it back in. What was u? U was x over 3 plus c. So that was really different. That was a really kind of backwards way to do it. But the reason I did it that way was to show you, if I didn't tell you what u was, how would we be able to get there? And the question would be is, what would I need to factor out in order for this to end up being a just a u squared plus 1? That's what I want to turn it into. To work forwards, u is x over 3. du is 1/3 dx, and so 3 du equals dx. So that's why we put the 3 out in front. And then what was x? What's the thing that we're squaring? X is 3u. So that's where the 3u comes in here. Square 3u, and I get 9u squared. And so the 9 can get factored out, brought outside of the integral, and oh, look at that. All we have left is my derivative of tangent inverse, which is where we wanted to end up. That's the problem worked forwards. Again, tougher problem. Probably the one that when we go through homework and people ask homework questions, this is the one they most commonly ask about is, how on earth do I figure out what to make u? And the key idea is that you want to think about what needs to go in here so that this number out here is going to factor out. I want this 9 factored out. How do I get there? That's the way that this is going to work. All right. Let's do one that is still a little bit tricky. It's a little bit harder than it first appears. And that is part C. We skipped this one earlier. Because what it seems like is that we should just make u equal 4x plus 2, and then du should be 1/4 dx, which means 4 du equals dx. And so then I have 4 times the integral of tangent of u du. And then all we have to do is take the antiderivative of tangent. Busted. We don't know the antiderivative of tangent. That's too bad. That's really bad news. And this is the reason that it's trickier than it first looks. Because we don't have a rule that when I take the derivative, the answer is tangent. So we need a different strategy. And this is where our u substitution is going to come in. This equals the integral. Let's rewrite tangent in terms of something that we definitely have a rule for, which is sine and cosine. And we know that tangent is sine over cosine. And now we can do a u substitution. U is cosine. Du equals, let's make sure we do this right. A couple details to be careful of. Derivative of cosine is negative sine. And the other thing we want to make sure when we take the derivative here is that the 4x plus 2 is inside of here. So we need to remember the chain rule times 4. Derivative of 4x plus 2 is 4. Oh, I don't have a negative 4 here, so it's not matching my sine of 4x plus 2 dx. So let's move it to the other side to make it match. Sine of 4x plus 2 dx. Now, I'm going to go through the rest of this problem. But while I do that, what I want to talk about is why did I choose cosine and not sine? The reason I chose cosine and not sine is because we want to keep our sine and dx on the top here. Because if I chose sine to be my u, then I would have du end up on the bottom of the fraction. And I don't want du to end up on the bottom. I want it to stay on the top where it is. There's a negative 1/4 out in front. Negative 1/4. So we substitute it back in. So this time, the reason I picked the cosine, and I also did this on, if you go back in the first problem we did today, I picked the cosine because then du ended up staying on top where I would like du to stay. Let's substitute back in. What was u? U was cosine of 4x plus 2. Let me give it a bit more space. So technically, you could memorize the antiderivative of tangent as natural log of the absolute value of cosine. But I'm not going to make you do that memorizing. I don't think it's worth it. I think it's just easier to just do the u substitution rather than memorizing this complicated thing and then not remembering where it comes from. Plus C.